Hey there, you've seen the periodic table a million times, right? But have you ever really looked at that huge block of elements right in the center? Well, today, we're taking a tour of that hidden world. We're talking about the most colorful, most powerful, and honestly, the most interesting elements of them all. Let's dive in.
I mean, you see them there all the time. That big chunk in the middle and those two rows just kind of floating at the bottom. Why are they set up like that? What secrets are these elements hiding in plain sight? That is exactly what we're going to figure out together in this explainer.
All right, our first stop on this tour is right in the heart of the table, groups 3 all the way through 12. This whole section is known as the D block, but you probably know them as the transition metals. And you can think of them as this crucial bridge that connects the two very, very different sides of the periodic table. So, what's the official entry ticket to the Transition Element Club? Well, it all boils down to their electrons. An element gets the title if it has a D subshell that isn't completely full, or, and this is important, if it can form an ion that has an incomplete D subshell. This unique electron setup is the key to everything cool about them. It's what lets them be that perfect bridge between the superreactive metals on the left side and the more chill nonmetals on the right.
Okay, now this is where things get a little weird, in a good way. Take a look at chromium and copper. You'll see their actual observed electron configurations. They don't match what we'd expect based on the rules. It looks like an electron from that outer S shell actually jumped down into the D shell. Now, why on earth would it do that?
And here is the secret. It is all about stability. You see, atoms, just like pretty much everything in the universe, want to be in their most stable, lowest energy state. And it just so happens that having an electron subshell that's exactly half full, like what happens with chromium, or one that's completely full, like in copper, well, that's an extra stable arrangement. Nature will literally bend its own rules to get that extra bit of stability.
And that unique electron structure gives these metals a genuine chemical superpower, the ability to have variable oxidation states. What that means is they can lose different numbers of electrons depending on what they're reacting with. This makes them incredibly flexible and useful in all sorts of chemical reactions.
And this chart shows that flexibility perfectly. Just look at manganese. It can have 6 different oxidation states, going all the way from a +2 to a massive +7. The reason it can do this is because it has 5 unpaired electrons hanging out in its D shell, giving it the maximum number of electrons it can possibly share or give away. It is the undisputed king of chemical versatility. Of course, outside of all this tricky electron business, these are the elements that pretty much define what we think of when we say metal, right? They're strong, they're shiny, you can hammer them into thin sheets or pull them into long wires, and they're fantastic at conducting heat and electricity. These are the elements that form the alloys like stainless steel and bronze that we literally build our modern world with.
Okay, so we've explored the bridge. Now it's time to head off the mainland and venture into that mysterious territory set apart at the very bottom of the table, the F block. This is home to the inner transition elements.
So why do we call them inner transition elements? Well, it's because their final electrons are filling up the f orbitals, which are buried even deeper inside the atom than the d orbitals we were just talking about. And their weird placement, honestly, that's just for looks. If we put them where they actually belong, tucked into periods 6 and 7, the periodic table would be incredibly long and awkward to fit on a page. So we just pull them out and put them down below. Let's start with the top row of the F block, the lanthanoids. Now, this is a series of 14 elements that follow lanthanum, and they are famous, or maybe infamous among chemists, for being almost frustratingly similar to each other. A big reason for that is a really fascinating phenomenon we need to talk about. It's called the lanthanoid contraction. Here's the deal. As you move from left to right across this series, the atoms actually get smaller. Now, that seems totally backwards, right? You're adding more protons, more electrons. Shouldn't they get bigger? Well, not quite. Here's the crucial detail. As the nucleus gets more and more positive, the new electrons are being added to that deeply buried F subshell. But it turns out F electrons are just terrible at their job. They're really bad at shielding their fellow electrons from the pull of the nucleus. So with each step you take, that stronger nucleus just pulls all the electrons in a little bit tighter, causing the entire atom to actually shrink. Now, I know what you're thinking. A bunch of obscure metals that shrink? Who cares? This all sounds pretty abstract. But this one weird property leads to an application that is, quite literally, lighting up your face right now.
Yep, that's right. The incredibly vibrant reds, greens, and blues on your phone, your computer monitor, your TV, they're all created by tiny little patches of different lanthanoid compounds. When you hit them with a beam of electrons, they glow with these brilliant, very specific colors. So every single pixel on your screen is a little tribute to the bizarre physics of the F block.
Now let's move down to that second row. Meet the actinoids. And if the lanthanoids are like a family of very close siblings, you can think of the actinoids as their heavier, much more unstable and radioactive cousins. The number one defining feature of the actinoids is this: every single one of them is radioactive. No exceptions. In fact, most of them don't even exist in nature. They've all been created by scientists in labs. They're also incredibly dense. And unlike the very predictable lanthanoids, they show a huge variety of oxidation states, which makes their chemistry way more complex. So, we've got these two rows of inner transition elements, the lanthanoids and the actinoids. Let's put them side by side to really nail down the key differences and, more importantly, what those differences mean for us. Okay, the biggest dividing line here is radioactivity. Lanthanoids are, for the most part, stable. Actinoids are not, and that one fundamental difference completely dictates how we use them. The stable lanthanoids end up in our consumer tech, our screens, our speakers, powerful magnets. The unstable actinoids, on the other hand, are used for things that take advantage of that instability, like in nuclear power plants or that tiny, tiny bit of americium that's inside your smoke detector.
And this chart just makes that difference in their chemical personality crystal clear. You can see the S-block metals are pretty simple. The lanthanoids really prefer to be in that +3 state. But then look at the actinoids. They have this huge, complex range of possibilities, which actually makes them act a lot more like their relatives back in the D block.
And you know, how we even figured all this out is a great story of scientific courage. When Glenn Seaborg first proposed this layout for the actinide series, it completely went against what everyone thought was right. People warned him it could ruin his career, but he believed in the data, published it anyway, and completely reshaped the periodic table into the one we all know today.
So, there you have it. From the super versatile D-block metals that build our cars and bridges, to the flock elements that light up our digital world and power our cities, that middle section of the periodic table is anything but boring. It's really a map of discovery, and believe it or not, there are still blank spaces left to fill in. And that really brings us to a final mind-bending thought. We are creating these super heavy elements, one single atom at a time, in massive particle accelerators. The story of the periodic table isn't finished. As we keep pushing the absolute boundaries of physics, what new chemistry, what strange new properties, and what incredible surprises are just waiting for us to discover?